In this lecture, we are going to learn how to assign a point group to a molecule. A point group is essentially a summary of all of the symmetry elements that are present in a particular molecule. And so we've learned all of the potential symmetry elements that are present in a molecule. So I'm going to use this cube here just as a summary. And so we have mirror planes, and so this of course has several ways that you can cut into half, but if you can have a mirror plane, a plane of symmetry, and insert it through the molecule, that's one of them. You can have axes of rotations, and so there's several different mirror planes here. I just wanted to show you one. We also have one that goes through here, cuts it into half this way, sideways. So there's tons of in fact, the cube has 9 different mirror planes. Axes of rotations, if you can put an axis anywhere through this box, and so we can put one through the center here. That would be a 4-fold, a C4, but we also have C2s, so we can have it through here, or we can actually have C3s that go through here. Okay, and that's important, and that we differentiate between the different axes of rotations. And we also need to assign the marrows. They're either vertical or horizontal with respect to the principal axis. And so if we make this the principal axis, then the mirror plane that I drew here first would be along that C4. It would be considered a vertical mirror plane. And then if we draw a plane here like this through the center, that would be a sigma H, a horizontal mirror plane. An inversion center is simply a dot, and so there would be one here in the middle. So it's a point through which all of the matter projects into itself. So it's easy to see that we have an inversion center here. And identity is a 360-degree rotation, and then the improper rotation would be and so there's an S4 here. You can do a 90-degree rotation followed, so that would be a C4 followed by a sigma H, and that would be true for the cube as well here. So I have a third backup cube, but if you're interested in looking at all these different symmetry elements, and for a cube, it can be kind of a fun exercise. I'm going to make one last point about the vertical and horizontal mirror planes. So they are, as I said, they are with respect to the principal axes. So here we have C4, C4, and C4. So we have actually 4-fold axes, C4 axes. And so if I, for example, make this one my principal axis, then all of the marrows that are vertical, so with these marrows that are through these faces here, there's 3 of them. If my principal axis is this, then this would be a sigma V, and this would be a sigma V, but this would be a sigma H, okay? And then actually, if I do these mirror planes, now they're neither vertical, and that can be a scenario also that occurs, and so you won't have to differentiate them. But if that's the case, if we have so many different mirror planes, and these would be here vertical, definitely vertical, and so this one is neither horizontal, so these are question marks. And usually what we do is we call them then sigma Ds if we have mirror planes that are that have different orientations from horizontal or vertical. But that's just in case you come across a sigma D. You will never have to differentiate or assign that, or you will need to know how to assign a sigma V or sigma H. Okay, so we are pretty much ready to do so. So here we have 2 molecules. They're pretty simple. They both have the same symmetry operations if you go through it. So there's a C2, okay, and then we have 2 mirror planes. And I'm gonna have a hard time, but the other mirror plane in this case, right, we have the 2 lone pairs here. One, if you wish, one comes up and one goes here, and so here instead we have these 2 two chlorine atoms attached where the lone pairs would be. So that's gonna, so we have the second mirror plane that's this way, and then we also, so we have a sigma, we have two sigma v's, and then also everything has an identity. Don't forget. So those are the four symmetry elements that are present in both of those molecules. And if that's the case, then the point group, they're in the same point group because they have the same symmetry and they will have similar. And when we're all set and done with it, we're going to just look at what we can potentially do. We're going to look at IR and Raman bands that we can calculate, at least how many we have. And then we're going to move on because this course isn't supposed to be designated or dedicated to point group theory. We are ready to assign a point group to these two molecules. You're going to need a flow chart. I will make one available to you. You can also simply Google symmetry flow chart and you'll come up with something that looks like this, or it might look differently. The principle is the same. You start at a point and you follow through until you get to your designation, and then you can assign a point group. So the reason I have this up is because that's what I was given as an undergrad when I took the course you're taking right now, and I just kind of like it, but they all are the same. So go ahead, print one out or bring one up on one of the tabs as we go through these molecules. So we start up here, and what I'm going to do is I'm going to cut this off here and put it side by side so you can look at it a little larger. If you're looking at it on your phone, it'll make things just slightly easier, I'm hoping. So that's what you're going to see, right? I'm going to put it like this and we'll go through it and assign it. So you start up here, as I said, and so the very first question, so your journey could be very short, right? If you have a linear molecule like carbon dioxide. Whoa, yeah, carbon dioxide is going to have a triple bond, that's for sure. Or carbon monoxide, which actually does have a triple bond. Those are linear molecules. Anything that is linear has a C infinity. Any stick's going to have a, well, you know, sticks are not perfect. But so this is going to have a C infinity. So is this. So yes, it has a C infinity. So the next question is, does it have an inversion center? The carbon dioxide has an inversion center, so that's a yes. So you end up at the D infinity H. So your point group is D infinity H for carbon dioxide. But carbon monoxide does not have an inversion center, right? So carbon and oxygen are not the same atom. So this would be a C infinity V. So it can be a pretty quick journey, but let's just go through it with the water molecule or the dichloromethane. Either one, they should have the same point groups. So first of all, these are not linear. They do not have a C infinity, so the answer is no. And so the very next question is, well, does it have anything higher than an identity or a 360-degree rotation? So this here establishes the principal axis. So Cn, and we already know we have a C2, so this is going to be our principal axis. So n in this case is going to be 2. If it was the cube, we would have choices, but not really, because you, out of the C2s and the C3s and the C4s, you would have to assign the highest one. So you would pick one of the C4s, then in that case n would be equal to 4. Either way, that's of course a yes. So we have anything higher than a C1, we come over here into the higher symmetry block, and for water, and we know we don't have a C5, we don't have a C4, we don't have a C3, so we come right down to the higher symmetry, to the lower symmetry block, and we have to answer this question. But before I do that, let me just go back to the cube. And so for the cube, we would get to this question. Yes, we have a C4, and not only do we have to have 1, we have to have 3, which we know in the case of the cube. We're fine, but I'm getting distracted from what we are doing here. We have a C2, our n was equal to 2. So we are down here at this question, and so this is, what does that even mean? Okay, we have NC2, funny symbol Cn, right? We know that n is equal to 2 in our case, so we are looking for 2 C2s, this means perpendicular, that are perpendicular to the principal C2. Okay? So if our principal axis was a C4, or n is equal to 4, then the question would be, are there 4 C2s perpendicular to the principal C4 axes, right? So you just have to replace n with your principal axis. And so in our case, we know we only have one C2, and so the answer is no, but they would of course be somewhere here, and that can't be because it would rotate those hydrogens up. Then, so we have a no. The next question is, do we have an S2N? N is equal to 2, so this would be an S4, and so an S4 would be a C4 followed by a sigma H, and so we know we don't have that, so we're going to go down this way. And also, if you're not sure, if you're not sure if there is like a C4, an S4, so we're looking for an S4, or if you come to that question and you're not sure, you think maybe there is one, but you're not sure, go with no. You'll do well. These point groups are rare. Of course, I'm going to sneak one in on the exam, so there's that. So you can't be sure if you can go with my advice or not, right? So it's your call. Okay, so in this case, we don't have an S4. We also don't have a horizontal mirror plane, but we have 2 sigma V's, and so that are, and so this becomes then a C2V point group. So both of those are C2V. So now you know how to use the flow chart, and so we're going to go through all 6 of these. I suggest that you pause, you go through it, and then I will go through assigning the point group rather quickly. We already know we have a C2V, so let's go on to the next one. So this one has a C3. So no C infinity here, but we have a C3. We come over here, we know, okay. Do we have more than one? No, there's just the one. So we come down here to the lower symmetry block. Now we're looking for 3 C2s that are perpendicular to the C3. So they would be here. You know. And so if you look at that molecule from the top, for example, which also helps to find the C3, if you're looking at it from top down, you can nicely see your principal axes. The potential for you to have C2s would be through the hydrogen-nitrogen bonds, but because this is pyramidal, that doesn't work, right? So any of the C2s would bring these hydrogens up, and so we do not have a perpendicular C2s. We don't have anything other than the one C3. Do we have an S6? We're just going to say no. Do we have a horizontal mirror plane? Well, that's going to be tough if again, for a molecule like this, it would have to be here, and then that would again bring up all of those hydrogens. So we have a no. So no. Sorry, we already said no here. We don't have a sigma H, and so do we have any sigma V? So are there any other mirrors here? And the answer is yes. There are 3 mirrors, and they are through here, here, and here. So those are your sigma V's, and I'm drawing lines, but those are obviously planes, okay? And they go up and down through the ammonia molecule, and so we end up having a C3V point group for that. This next one is FLED. It's trigonal planar. Again, it is not linear, so that part is easy. We have a C3. The C3 goes through the boron, so we're looking right at it. So there's a C3 here. So N is going to be equal to 3. We don't have more than one, so we can skip right through the higher symmetry block. And now we are looking at perpendicular C2s, and they have to be 3 of them. And in this case, we do have them because this is flat. It's just a triangle, and so we have a C2 through here, and a C2 through here, and a C2 through here. So the answer is yes in this case. And the next question is, do we have a horizontal marrow plane? Absolutely we do, because you got to remember your principal axis is through the plane here, through the paper. It pokes right through the boron and comes at you. And so this marrow plane is horizontal with respect to the C3. So that brings us to a D3H point group. Okay, that is more symmetrical than the one we just looked at. We already did this one, right? We have a C infinity and we have an inversion center. And so that would be a D infinity H, D infinity H. Okay, so if I draw hydrogen peroxide this way, then you should assign a point group this way, yeah, right? So there are several C2s here, and there's one through here. Actually, there's just one C2 here. Okay, so I take that back because you don't have one here. You'd project that into there. So there's only one C2 that I see at this point. It goes through the molecule like that, which rotates it this way, right? So everything rotates accordingly into itself or into another atom of its kind. So we do have a C2, and so we're down here, no infinity. We skip right through this because C2 is our highest, and now we're looking for perpendicular, and I already ruled them out because I said you cannot have a C2 here. That doesn't work. And so we have a no. Now we're looking for an S4, right? So the best way to do this is, and the answer is no, there's no S4. If you didn't find one, you know, if you could rotate this 90 degrees, but then it would project also your hydrogen into this plane perpendicular to the board, and so there's a no. And then the question about the sigma H is yes, and that's because the plane here, so I'm gonna redraw it. The plane we have, the C2 is here, so this would be a sigma H, right? And so we have a C2H. That's a C2H. If we rotate that 90 degrees, we get a different point group, right? So now we have still have a C2. It's this way. We skip through the higher symmetry box. We come to the perpendicular ones. Again, that's easy to rule out. No perpendicular ones. We probably don't have an S4. And so a horizontal marrow plane now would be here. Okay. And the answer is no. These marrow planes that we see now, the plane is not along the C2. It's cutting the C. Actually it's along the C2. It's not cutting the C2 in half. So the C2s that we have are the sigmas that we have are going to be vertical. Okay, so sigma V and sigma V, and so this is also C2V, just like water was. And so I'm not going to practice all of these with you. You can do some of them. I'm probably going to do, well, I am going to do like 3 of them. I'm going to do these 3, but you should do the others on your own. And then here are some from a quiz that I've given previously, so you can use those to practice as well. The reason I want to do this one is because it's a tetrahedron, and again, I'm trying to sucker you into thinking it's flat, but you're smarter than that. You know, it's a tetrahedron. So it's best to build that. And so let's go through these 3 and then move on. Okay. So this one has a C3. And it goes right through here. And hopefully you have no trouble finding that. If you do, you feel free to build that molecule. And so N is going to be equal to 3. We do not have more than 1. And anything perpendicular would put this out of whack. So that's a no. And then we would have to have an S6. So that's also going to be a no. And then we are looking at horizontal marrow planes. Horizontal marrow plane would also have to be here. You know, it has to cut that C3 somehow, and so that's a no-go as well. But then we have these three mirror planes. So if you draw, I'm going to draw it like this now, where the hydrogen is up top, and 1, 2, and 3, the chlorines are here. So your C3, this way you can see it's oriented in the way where you can find, and so we have these planes that are going through these chlorine, carbon, and then hydrogen. It goes through that plane, and so there are 3 of them, and I do believe we do need actually 3, so there might be actually a problem here with my flow chart, or N sigma V. So we have a C3V, right? So if you're looking at a trigonal bipyramid, you have the potential to have 3-fold axes and 2-fold axes. There's high symmetry here, and draw it in a way where you can make sense of it, where you redraw it. And I like this. I can see here I've got the trigonal base that's cut in half, and I have the 2 pyramids up top and the bottom. And so I don't have a C3. I would have to have the equatorial atoms would have to all be the same, but we have chlorine and fluorine, and so there isn't one. And then so the potential for C2 is through the phosphorus fluorine bond, right? The 2 chlorines would project into themselves, but because our 2 axial atoms are all also different, the fluorine would project into the chlorine. We do not have a C2, but any trigonal bipyramid you should consider could have a C2 or a C3. In this case, we actually do not have any axes of rotation, so here the answer is no. And so now we are asking ourselves, we just need to find a single mirror now, okay? And so the mirror that we have is through the fluorine phosphorus, and it's hard to draw, right? Because this sticks out. If I redraw that, and this comes back here, right? So if I redraw this and put the chlorine, fluorine, and I now put the other fluorine here, and then I draw the 2 chlorines here. Now it's a little easier for you to see. I know it's very sloppy, but it's a little easier for you to see that that plane here would dissect, so the chlorine would project into the chlorine. So there is actually a sigma here, so it is a CS point group, okay? So they can be tricky, and you need to find a way that works for you where you can see the potential axes of rotations, and if it means for you to assemble a molecule, you should probably go ahead and do that. So here we have an octahedron, and I've redrawn this molecule in 2 different ways. So I'm going to draw it randomly on paper, and you need to realize that you can have C4s, you can have C3s, you can have C2s through a perfect. You can put it into a cube, right? So it's very much like a cube. In fact, if you had a perfect cube, you would, and if all of those ligands were the same, you would have an octahedron, and guess what point group that would be in, right? So just for fun, since it's related, let's do the octahedron, a perfect octahedron here, right? We already know about all of those sigmas and whatnot, right? So we would have a C4, and we would have 3 C4s, and we would have an inversion center, so a perfect octahedron would be in an OH point group, right? So what that means is for this octahedron is that we should know where those axes are, right? And so you can orient, so we have 3 and 3 ligands here, or positions on the tungsten, and so there's 2 different ways to draw that. There are 2 different isomers actually. So, and if I was to redraw the other isomer, I would put the chlorines all in a plane, okay, and the hydrogens would be in the plane. So this we call the meridial conformation. Cis and trans, this is meridial and facial, and this would be facial, okay? And then it's just because I've drawn it differently, here, different orientations, doesn't mean they're different structures. These are the exact same structures. They're just rotated a little bit, and so the chlorines are facial. If I was to put this molecule into a box, the axes would go through here, and the two hydrogen atoms would be here, here, and here, right? So this may be very difficult for you to see. Go to one of those websites, but so their C3 is there, and so in this case we do have a C3 that goes through here. Okay, so no infinity, of course. This is a C3. Obviously I had a hard time finding one, so there's probably not going to be 4 of them. And then you have to ask yourself if there are perpendicular C2s, and I'm going to have to find a whole bunch of them. The answer is no. And then we also don't have a horizontal mirror plane. It would have to go through here because remember we have the C3 here now. But we do have vertical mirror planes. We have several, and so this is also a C3V. All right, so you do need to practice this, I am sure. Let's take a look at some more complicated molecules here. Also, we have an octahedron here, but we have these so-called chelating ligands that are connecting 2 of the positions, okay? And so I talked about facial and meridial. These are, of course, you can have cis and trans, and these ligands cannot go trans, right? So if you have cobalt like this, you cannot have a chelating ligand that goes across, only in the cis position. And I'll show you a picture later. This kind of forms a propeller, so it's really difficult to see, but there still is a C3 through that. I do have a molecule. Let's take a look at that here, right? So this is the octahedron with, and so you do want to look down that one position, and you do actually have a C3. This is like a propeller, right? A propeller has symmetry. This is a propeller with 3 blades, and so we do have a C3, okay, that goes. It's hard for me to twist that properly, but it is there. So okay, so there's a C3, and I'll come back to that in a minute. There's also perpendicular C2s. So here we only have one chelating ligand, but there's a C2 there, okay? It projects this blade into this blade, okay? But that's all there is, and there's also no mirror planes. That destroys the mirror plane. If we have 3 of these blades, we do have C3s, but we also have perpendicular C2s that are through here, okay? All right, but again, we still don't have any mirror planes, and that makes this molecule a chiral. The lack of mirror planes will make a molecule chiral, right? So if we only have C2s or C3s, a single axis of rotation or multiple axes of rotations, we have a chiral molecule, right? So we have, think about a screw, a left-handed and a right-handed screw, or a left-handed and right-handed propeller. That's exactly what this is. And, so for you to see the C3 a little better, you might want to draw a triangle through. See, these come to the front. All of those, if you wanted to, you could say, well, these 3 are facing me. This is a facial orientation I'm looking at. And so if I draw this triangle, you can kind of see how, this goes into the back, this comes into the front. When that rotates, this nitrogen rotates into this nitrogen, and this simply stays in the back, but they are still connected. You still have that chelating ligand. So that can be very tricky. I don't know if this helps. And I did want to show you one other thing about the octahedral. So one way to draw it is the way I've kind of done it, and you want to find your way of drawing it. So this is one way to draw it. And so if you want to then put your facial ligands together, or meridial, so here I think you can kind of see that, right? So where we have these things coming towards us, and then they go in the back. There's another way to draw it, where now we have 3, and that works very well as well. I do actually like this way of doing it. And so now if you wanted to put your chlorine ligands here facial, they're right there, and it's just, and then you can draw it like this. And so whichever way works for you, you're gonna have to figure that out. So we just discussed that if you have a lack of meroplanes, you have a chiral molecule, and so the point groups are C1, Cn, or Dn. If you recall, we had of course you recall, it was just 3 seconds ago, right? So we had the one that was like a propeller. It had a C3, but it also had the C2s. So C3, and then it had several C2s that are perpendicular to the C3, and so that would be a D3 point group, and it would be chiral. So you'd have a left-handed and a right-handed propeller. And then we had the other one, which only had 2 chelating ligands, like that. And so this one had a C2 through here, but it didn't have any perpendicular C2s or any other symmetry other than that C2, and so this would be a C2 point group, and it would also be chiral. Okay, and this is maybe a nice illustration here of that D3 symmetric structure that we just looked at. So those are the mirror images, and so maybe you can build it or go to some online tool and see that they really do not overlap. I've got a few fun things here. Here's another example of a C2 symmetric molecule, and I actually built the two enantiomers, so they're not superimposable, and there's just a C2 through here. And actually, kind of too bad that we don't have an in-person. I usually have these 80 little structures for a lab that we go through and assign point groups. It can be quite helpful, but I'm sure you'll manage. And then finally, before I move on to the next part, we can also put molecules into a group that is polar. So now we're looking for, we can have meroplanes, but we can't have horizontal meroplanes, and we cannot have an inversion center. So if your molecule lacks an inversion center or a horizontal meroplane, it's going to be polar, unless of course we don't have polar bonds, right? So anyways, you know all this already, and when we get back, we are going to take this one step further. So brace yourselves.